Hello and welcome. Now we change the perspective and try to explain how rotor blades are really designed, and therefore we change the perspective from the complete rotor blade to a single element of a rotor blade. That means in these videos we would like to explain how to realize equal flow relations at each of the single blade elements. And therefore we change the perspective from this complete turbine to a single part of the rotor blade.
In this picture you can see a wind energy plant, and the wind is coming from ahead in that direction. The rotor blades rotate counterclockwise in the XY plane, and you can see a cross section in the left rotor blade. Here in the right picture you can see the same cross section, but a bit bigger and slightly rotated around the Y-axis. The wind is blowing from the left side in that direction again, and this makes the rotor move downwards in rotating direction. Here in this picture a cross-section of the rotor blade is shown again. With the help of this picture I will now explain the relevant velocity vectors for one blade element. And the red arrow shows the axial velocity VA. This velocity has the same direction as the wind velocity. And the blue arrow shows the circumferential velocity U. This velocity has the same direction as the rotating direction. And the green arrow shows the relative approach velocity, which is resulting from U and VA. And in yellow, the angle of attack alpha is shown. This is the angle between the resulting velocity VR and the profile chord. And this angle is an aerodynamic dimension. And in purple you can see the local pitch angle theta. This is the angle between the profile chord and the velocity U. And this angle is a constructive parameter. It differs for every blade element. On this slide you can see one rotor blade. At three different positions a cross-section of the rotor blade is shown. First at the rotor tip, then in the middle of the rotor, and also close to the center of the rotor. I will now present the relevant velocity vectors for these three positions. The red arrow shows the axial velocity VA. This velocity is 2/3 of the wind velocity when we are dimensioning according to Betz. And the velocity VA is the same at every blade element. And you can see this when looking at the lengths of these arrows. The blue arrow shows the circumferential velocity U at three positions. This velocity is calculated by the angular velocity omega multiplied with the radius r of the corresponding blade element, respectively by the tip speed ratio multiplied with the radius r of the blade element and divided by the total rotor radius and multiplied with the wind velocity. And you can see the radius r here in the picture. And the radius r is the distance from the center of the rotor to the corresponding blade element. The circumferential velocity u depends on the rotor radius r and thus increases towards the blade tip. And you can see this when looking at the lengths of the blue vectors. Here you can see the relative approach velocity VR in green for the three cross sections. This velocity is calculated by the square root of u to the power of 2 and VA to the power of 2. And this velocity also depends on the radius r, and thus it increases towards the blade tip. In this picture, the local pitch angle theta is shown for each cross section. This angle is a constructive parameter, and thus we are looking for this angle when dimensioning a rotor blade element. And there is a boundary condition that has to be taken into account when defining the local pitch angle theta. The boundary condition is that the angle of attack shall be the same at every blade element in order to achieve equal flow distribution at every blade element.
So We have here several angles, and here, for example, we have the delta that is equal to the sum of theta and alpha. And also we can describe the cosine of delta is equal to u divided to the relative velocity vr. And when we consider now again the complete rotor blade, and we see that the angle delta is increasing and increasing the closer we get to the hub. And when we also take into account that the alpha is constant, because we would like to have equal flow relations at every single blade element, we also can see that the angle theta is also increasing the closer we are getting towards the hub. And that explains why rotor blades have this spinning form over the complete length.
And you can see the twist of the rotor blade in these two pictures. In the left picture, you can see here that the blade is twisted, and in the right picture, you can see the twist here at this rotor blade. And in the next video, we will learn which forces arise on the rotor blade and how we can determine the optimal blade depth. So, thank you very much.